Have you ever wondered how an image, like the Mona Lisa, travels across networks from a distant server to your computer? Let's explore how the image reaches the client in a network that spans multiple routers and networks. In most networks, devices like the server and the client are behind network address translation. NAT allows private IPs to communicate with public networks like the Internet. The image data, like the Mona Lisa, is encapsulated into IP packets. Each packet has a header containing essential fields that guide the packet across the network. The version field, set to 0x04, indicates that this is an IPv4 packet. The Internet header length, or IHL, is 0x05. This specifies that the header is 20 bytes long, the standard size for IPv4 headers. The total length field is 0x0438, meaning the entire packet, including the header and data, is 1080 bytes long. The identification field, set to 0x369b, uniquely identifies this packet for reassembly if it gets fragmented. The flags field is set to 0x2, which means this packet is not fragmented and it's the last fragment. The fragment offset, set to 0x00, shows that this packet is not fragmented or is the first fragment. The time to live, or TTL, is 0x40, which equals 64 hops. This limits how far the packet can travel across the network before being discarded. The protocol field is 0x06, indicating that the transport protocol is TCP, although for this explanation, we are focusing on the IP layer. The header checksum, set to 0xA362, ensures the integrity of the IP header by detecting any errors that occurred during transmission. The source address is 0x0000001, or 10.0.0.1, which is the private IP address of the server inside its local network. The destination address, 0xC0F81666 or 192.248.22.102, is the public IP address of the client's network, before NAT is applied by the client-side router. Finally, the data section contains the actual image data, in this case, the Mona Lisa image. Before sending the IP packet, the server checks if the client is on the same local network. It does this by comparing the client's IP address to its own using the subnet mask. The server's IP address is 10.0.0.0.1 and let's assume that the subnet mask is 255.255.255.0. The client's IP is 192.248.22.102, which belongs to a different network. Since the client is on a different network, the server sends the data to its default gateway, router R1, to route the packet to the client. Since the server needs to send the packet to router R1, it first checks its ARP table for the MAC address associated with R1's IP address. The server doesn't find an entry for R1's IP address, so it broadcasts an ARP request. Let's break down the ARP request packet that the server sends to find the MAC address of router R1. The first field in the ARP request is the hardware type. It's set to 0x0001, which indicates that the request is being sent over Ethernet, the most common hardware type in ARP. Next is the protocol type. This field is set to 0x0800, meaning the ARP request is asking for the MAC address corresponding to an IPv4 address. The hardware address length is 0x06, indicating that Ethernet MAC addresses are 6 bytes long. The protocol address length is 0x04, indicating that IPv4 addresses are 4 bytes long. The operation field is set to 0x0001, meaning this is an ARP request. In other words, the server is asking, who has the IP address 10.0.0.0.254? The sender hardware address contains the MAC address of the server sending the request. In this case, it's 00:11:22:33:44:55. The sender protocol address contains the IP address of the server, 10.0.0.0.1, so the recipient knows who sent the request. The target hardware address is set to all zeros because the server doesn't yet know the MAC address of router R1. Finally, the target protocol address is set to 10.0.0.254, which is the default gateway. This is the address for which the server is trying to find the corresponding MAC address. Before the ARP request can be transmitted on the network, it needs to be encapsulated in an Ethernet frame. Let's explore how this happens. The ARP request is placed inside an Ethernet frame, which provides the necessary information for data transmission on a local network. The first field is the destination MAC address. Since the server doesn't yet know the MAC address of router R1, it sets the destination address to the broadcast address. This ensures that all devices on the local network receive the ARP request. The next field is the source MAC address, which is the server's MAC address. This tells the receiving devices where the frame came from. The EtherType field is used to indicate the protocol being carried inside the frame. For ARP, the EtherType is set to 0x0806, which tells the devices that the payload is an ARP request. After the Ethernet header, we have the payload, which in this case is the ARP request itself. Finally, the frame check sequence, FCS, is added at the end of the Ethernet frame. This is a checksum used to ensure data integrity during transmission, checking if the frame was corrupted. Router R1 receives the ARP request and replies with its MAC address, allowing the server to update its ARP table. The operation field is set to 0x0002, meaning this is an ARP reply. In other words, the router is replying, I have the IP address 10.0.0.0.254. Sender hardware address and protocol address contains the MAC address and IP address of the router, which can be obtained by the server. Target hardware address and protocol address contains the MAC address and IP address of the server. Now the server can send the IP packet, which has the image data, to the router R1 using the MAC address of router R1. Once the server prepares the IP packet containing the image data, it needs to encapsulate this packet in an Ethernet frame for transmission across the local network. Let's look at the contents of this Ethernet frame. The EtherType field indicates which protocol is being encapsulated in the frame. Since we are transmitting an IPv4 packet, the EtherType is set to 0x0800, meaning the payload is an IP packet. The payload is the actual IP packet itself. This packet contains the image data encapsulated within IP headers. Other fields are same as explained earlier. Now that the Ethernet frame is complete, it's ready to be transmitted across the network to the next hop, router R1. Now, the Ethernet frame containing the IP packet is received by router R1. But how does router R1 know where to send the packet next? Routers use routing tables to decide the next hop for a packet. A routing table contains a list of network destinations and instructions on how to reach them. Let's see how R1 processes the packet. Router R1 receives the Ethernet frame. It extracts the IP packet from the frame, then examines the destination IP address, 192.248.22.102, the public IP of the client. R1 checks its routing table for a matching network for the destination IP address. It finds that the packet should be forwarded to the next hop, which is router R2, because the client's IP is not directly reachable from R1. R1 then encapsulates the IP packet in a new Ethernet frame. The destination MAC address is set to router R2's MAC address, and the source MAC address is set to R1's MAC. R1 sends the new Ethernet frame to R2. When router R2 receives the packet, it repeats the same process. It checks the destination IP address, looks up the routing table, and forwards the packet to the next hop. This process continues through routers R3, R4, and so on, until the packet finally reaches router R8. When the packet reaches router R8, which is the client's gateway, network address translation occurs. The router translates the public destination IP to the client's private IP, 192.168.1.10. Then R8 checks its routing table and sees that it is directly connected to the client's network, meaning it can deliver the packet to the client without needing to forward it further. Through this process of routing, the packet has traveled across multiple routers, each one making a forwarding decision based on the destination IP address and its routing table. Finally, the image data encapsulated in the IP packet arrives at the client. The client extracts the image data from the IP packet and reassembles the packets to display the full image of the Mona Lisa. This is how an image travels from a server to a client. It involves Ethernet frames, ARP requests, routing, network address translation, and the processing of IP packets. Thank you for watching.